Hello everyone. Today we'll be talking about bots, specifically the ones that commit code in various social coding platforms. I am Tapajit Day, a PhD student at the University of Tennessee, Knoxville, and I worked with Sara Mousavi, Eduardo Ponce, and Tanner Fry on this project. And we also collaborated with Bogdan Vasilescu from CMU and Anna Filippova from GitHub. This project was overseen by Audris Mockus. Bot adoption among software developers is becoming increasingly common. Bots are being used to take care of a number of tasks that used to be performed manually, like creating code commits, managing issues, and pull requests. GitHub actually has a dedicated topic for bots, and there are over 11,000 repositories matching this topic. There are also dependency management tools like Ependabot, which are being moved to GitHub. There have been a lot of research focused on bots also. Last year, there was a workshop on bots for software engineering. There have also been a number of articles on bots. And the second workshop on bots for software engineering will take place on July 2nd. We have another paper over there that talks about bot commits. So if you're interested, keep an eye out for that as well. Besides, not accounting for bots can lead to misleading conclusion when you are trying to estimate the effort, productivity, team size, repository activity, or something similar, since bots may generate physically impossible metrics of activity and productivity, or could at least significantly bias those estimates. So bots need to be removed from the datasets while investigating similar questions. Here is an extreme example of that. So a bot found a vulnerability in a dependency. A bot sent a pull request to fix it. A CI bot verified the pull request. The pull request was merged by a bot, and a bot celebrated that merge with a GIF. So that's how sophisticated bots have become nowadays, right? We can also see that bots are often among the top 3 contributors of a repository. For example, in this case, a bot named Scala Stewart made more commits to the repository than the creator of the repository himself. So, are you accounting for bots in your research? However, detecting bots is a task that is easier said than done. So our first goal in this project is to develop a systematic method for detecting code commit bots. And we are also trying to characterize the bots to find out the type of work they do and the languages they work with. So let's start with the task of bot detection. We have access to a massive data set containing information about all open source projects that use Git, called the World of Code, which was introduced in last year's MSR conference. The version of the data we used had information on over 73 million unique repositories, over 1.68 billion commits, and over 34 million unique authors. The author IDs in World of Code is based on a combination of their name and email address. However, trying to study bots from this massive data set limits our choice of algorithms due to the size and the processing time constraints. So we decided to use a combination of some heuristics and some fine-tuning. The first heuristics is based on the observation that many of the bots have the word bot in their names. So we used a regular expression matching to search for that. A few considerations we had to keep in mind were that the search should be case insensitive, and cases like a bot or botha, where the word bot is the part of a name, should be avoided. We also wanted to avoid cases where the word bot appears only in the domain name of the email address. However, this method by itself cannot catch all the bots. For example, you can see this bot, which will not be captured by this method. We call this method bot identification by name, or BIN. For more details, please see our paper. The second heuristics is based on the idea that many of the bot commits are actually created using templates, which has a combination of some fixed text and some variable text. For example, a bot named AutoBuildBot on Travis CI used the same commit message, update HTML, for all 739 commits it created. On the other hand, a bot named Common Workflow Language Project Bot used a commit message structure where the username, the software name, and the name of the person who created the change were the variable bits, and the rest of the message remained the same. For more details on the algorithm we used, please see our paper. We call this method bot identification by commit message, or BIM. The third heuristic is based on the observation that bots tend to update the same type of files. As you can see from the table, that the number of file extensions in the bot commits tend to be lower. Bots also typically make larger commits, meaning they have more number of files per commit, and they also tend to have a much lower variation in the number of files per commit. We call this heuristics BICA, or bot identification by commit association. That is, the files and projects associated with the commit. Finally, the result of these three heuristics is passed to an ensemble model to answer the final question: is the author a bot? We call this whole approach BIMAN, which stands for bot identification by commit message, commit association, and committer name. So as you can see, the structure is something like this. So we start from the world of code data, we extract all the authors and all the commits made by these authors, and then we create we extract the commit message, the files and projects associated with the commit, and we get the name and email address of these authors and use our three heuristics method, and finally pass them through the ensemble model. However, BICA uses a random forest model, as you can see from this workflow, and our ensemble model is also another random forest model. So we need some training data. However, we found no representative list of bots in literature. So we decided to create a ground truth data manually. We used bin on all the author IDs that we extracted from the world of code and identified a list of potential bots. Two of the paper authors verified the list and removed the ambiguous cases, which were less than 1%. And in this way, we found a total of 13,150 bot authors. To get a list of humans, we selected 13,150 authors from the rest at random and verified them to be human by the same two paper authors. Thus, our final dataset contained 26,300 author IDs, 50% of which were bots. So, how does our bot detection approach perform? BIMAN was able to achieve an AUC of 0.9, which is really impressive. And in this table, we are showing how it performed in identifying the IDs associated with 11 known bots. We found a total of 67 author IDs associated with these bots. BIN was able to identify 37% of them as bots. BICA could identify 79% and BIM 70%. Our ensemble model, that is our whole approach, BIMAN, was able to find 87% of them as bots. We were curious about the 9 that were not detected as bots. So we checked them out and found that 6 of the 9 are actually human IDs that were just using the same name. The 3 others just had 1 commit each, making any decision about them much harder. We also created a dataset with detailed information on over 13 million commits by 461 bots that we found, each with over 1,000 commits. This dataset has information about the author ID, the commit SHA, the time of the commit, the time zone, the files modified by the commit, and the projects the commit is associated with, along with the commit message for each of those 13 million plus commits that we have. This data is shared through Zenodo, and the link is available in the paper. Now we will quickly go over a few highlights from the bot characterization task. We found that a number of bots work at very regular hours, which is shown here by the radial activity plots. These plots show the relative activity of the bots at specific hours of the day. The hours between 8 AM and 4 PM are highlighted since most of the human activity occurs during these hours. We see that a number of bots are active throughout the day, which we call the continuous activity bots. And some of the bots are active only at specific hours, which we call spike activity bots. However, there are also some bots who are active when humans are typically active, suggesting that these are reactive bots responding to some activity of the human developers. So these bots are not active throughout the day. They are active only when humans are active. And also, there are obviously some bots whose activity patterns follow none of the described patterns. We call them others. For more details of the process of how we find these bots and how we characterize them, please see our paper. We also found that the bots tend to work with web-based languages like HTML, JavaScript, and CSS much more often. As you can see from the plot over here, that HTML is the language the bots most frequently work with, followed by JavaScript and CSS. Then we have Python, C++, and C, then Ruby, Objective-C, PHP, Java, TypeScript, C#, Swift, Rust, Vim script, and Go. This result was created by looking at the commits from the 13,150 bots that we manually identified. We extracted the languages from looking at the file name extensions using the linguist tool offered by GitHub. We investigate this aspect in further detail in our paper that will be discussed in the upcoming Bots for Software Engineering workshop. So if you are interested, please keep an eye out. This concludes our presentation. You can find the code and the fitted models in the GitHub repository link shown here. The link is also available in the paper. And do reach out if you have any questions. Thank you.